So let's go on with composite plates and wires. So in practice, that of course we have learned how to get the centroids of a triangle, of quarter circle, and arc circle. But in daily life, in reality, that the shapes are more complicated or more complex. The shapes are more complex, but it can be seen as the composite. Composite of plates of simple shapes. So, for example, for this 五边形英文是怎么说？有没有同学知道 how to say a shape with 5 sides? This is a 1, 2, 3. Oh no, this is a 4. This has only 4 sides, but 4 sides is in mathematics books that it is quadrilateral. Okay, 5 sides is pentagon. Very good, very good. Pentagon. Very good. And this has 4 sides, and but it can be okay. This is for 5 sides, and this is pentagon, and the 4 sides. If you look at the mathematics book, it is called quadrilateral. Should I mark it down? Quadrilateral. And I will say I will pronounce it as pentagon. Okay. Now, so how do we get the centroid of this shape or the center of gravity of this shape? Now, suppose that it can be seen as one triangle with centroid G1, another center a rectangle with centroid G2 and triangle with centroid G3. Now, if we consider MY, I think I mentioned last time. Consider is 考量. So consider MY is equal to consider MY. So MY is in this direction, right? So it is equal to moment arm times force and moment arm times force and moment arm times force. So it's this is x1 bar and this is x2 bar and so on. You know what? I think let me move this away and. This one is x2 bar and the last one is x3 bar. So the total moment about y-axis is equal to this one, right? This is the total moment. Now, if the centroid of the whole area is if the whole area, the center of the whole area is x bar here. So it should be equal to, and for this one is W1 plus W2 plus W3, right? Let me move this to here. So this is equal to W1 plus W2 plus W3 for this red arrow. So it should be equal to x bar times the total force, the total weight of the three parts. So in mathematics, it is written like this: x bar times bracket W1 plus W2 plus W3. Therefore, x bar is equal to x1 W1 plus x2 bar W2 plus x3 bar W3 over W1 plus W2 plus W3. So this is equation 5.7 at the bottom of page 240. 240, right. And to use this equation, look at the sample problem 5.1. On page 242. I will do a 3D version later. I will do a 3D problem later, but you can take a look at example 5.1. So we are using moments. So we are using the equivalent moment to write these two equations, and we compare these two equations. You get x bar here, and so this is if you want the equation on the book, this is on page 240. Now, take your time to write this down, and after you have write it down, then we go to the next page. So, and a very good question from very good question from your friend, that here in this chapter, because x itself is only a direction. X is a direction, so it does. So it is only a direction. It is not a value. So for all centroids, for all centroids in this chapter, I will write a bar over x and y and z, so that you know from, if you see this, that you know it is a centroid. Okay, because x itself is only a direction, so it is not a value. So here we have if we want to say the centroid in x direction, I would write x bar, so you know from here it means centroid. Okay. Now, before we take a break, let's let's work on sample problem 5.3. Here, a uniform semicircular rod. Semicircular means 半圆形. Of weight W and radius R is attached to a pin at A and rests against a frictionless 无摩擦 surface at B. Determine the reactions at A and B. Attached to is strictly speaking is 连附 So I'll talk about the English later. Any other words that you don't know? Rest 是静止。So so this is not. I think most of the words are fine. Now, so we go on with solving equation. So this is because it is at equilibrium. So and it's at rest and it is at equilibrium. So we need, before we write some equations, we need to draw free-body diagram. Here, the free body diagram looks like this, and with the free body is of course the semicircular rod. Oops, not very good. And I just look like this. Now, so we have points A, B, and we have centroid somewhere here. Now, what forces do we have here? What forces do we have? It has a weight. Remember, in this here we have a weight here, W. So it has a weight. So we need to draw the weight on the free body diagram from the center. How about at B? I'm sorry. Let's go from A. A is a pin joint, right? A is a pin joint, so it has. So it cannot move to the left and to the right. So it has an AX. It cannot move up and down, so it has an AY. But we will simplify later. So let me draw it here. In examination, if you are not sure what to do, draw your free body diagram first. How about what B? B is frictionless, so it can move free up and down freely. So it cannot move left and right, so we have only one force P here. I may draw a W a bit shorter. Okay, like this. Of course, you can. We have how many equations do we have? We have three equations and we have three unknowns, right? We have Ax, Ay, and B. So of course you can work from here. You can work from here and determine Ax, Ay, and B. This is perfectly okay in examination. But let's have a look. And can we say it is either a two-force body or three-force body here? We have four forces on the free body diagram. Is it a two-force body or three-force body, or it is something else? Three-force body. So because all forces act on A, B, or C, it is a three-force body. So we know the lines of action would. So all lines of action would cross at one point. So it means the lines of action between B and C is here. So it means the line of action of the resultant at point A would also go through this point. So we have force A here. Is that okay? Because it is a free force body, we can determine the direction of A in a straightforward way. Now, so suppose this afterwards that let's draw some. Before we take a break, let's complete the free body diagram. Here is x bar, which is equal to r sine alpha over alpha, which means it is 2r over pi. Here alpha is equal to half of pi, which is 90 degrees. And here we have the diameter, which is 2r. Therefore, tangent theta is equal to 2r over pi, which is equal to pi. Then I think we have completed the free body diagram. Then we take a break, and I'll explain it after the break.